All right, so today let's take a look at some combination between homological algebra tools and the way Oort presents Riemann-Hurwitz formula. I call this proactive learning and teaching, which leads to research. Vice versa, research involves learning and then teaching as a preliminary stage for better understanding the subject, as we all know. Feel free to look at the slides associated to this seminar. That would be slide 18 right now. And then this leads to upgrading mathematics. Which means looking at well-known results and then instead of just reproducing them with the same concepts and terminology and as in previous textbooks, articles, and so on, we update them with modern tools. And to be more specific, this Riemann-Hurwitz formula and related results corresponds to 1859 or 50s to 1935-ish, as it will be detailed today when looking at the corresponding results and how they evolved. And then if we add the category theory, which I'll call it cat language, and grothenic ideas, then it seems like we can separate from the geometry of Riemann surfaces a certain layer, abstract nonsense, if you want, belonging to homological algebra. For example, if you think of derived functors and so on. Here, I should mention as a key concept, integral schemes. Which marked the beginning of modern algebraic geometry. So if we add some basic facts and results of homological algebra, then we see that the rest from the geometry of Riemann surfaces is in fact some topology, where here we think more of if you want networks. networks, quivers in the algebraic realm. And one important theorem which is useful to make sense of say, geometry of Riemann surfaces from this point of view is Poincaré-Hopf theorem. Regarding indexes of vector fields and flows on manifolds which are restricted by the topology, rather global topology. So then we might be able to clarify even more the connection between number fields, which is the algebraic level, and function fields, which in some sense are dual. But these are things which I might mention, trying to understand them better later on. And it goes beyond the more specifics of Langlands program, very technical and somehow still classical. Let's see if we can make use of more of these boards. In the slide, I mentioned a few more specific points to recall. For example, what is the Euler-Poincaré map for a finite exact sequence, or actually for a finite chain? And then the other characteristic of the chain complex is the same as that for the homology, which is a pure algebraic result, which seems to be relevant to understand the homological algebra aspects of this Riemann-Hurwitz formula. And then think of the dimension as a classifying invariant for vector spaces over a field. And then when you consider a field extension, for example, number fields, then in particular, these are vector spaces. So it's a change of coefficients from a category of vector spaces over one field to a category of vector spaces over another field. And this is functorial associated to this extension as a morphism of fields. So there's a lot of category theory which clarifies and shows that there are some general facts which are independent on the particular context of these Riemann surfaces over some ground field. And again, this couldn't be recognized at that stage. And later presentations like Oort's presentation, which follows the historical development, does not include this upgrade or update. And that's what I'm trying to do here. And I call this a proactive learning and teaching approach. So let's go over the specifics from the Oort article. There were various stages for the Riemann-Hurwitz formula. Let's recall one of the first formulations due to Riemann-Hurwitz around 1850s, which I will rephrase it as follows. If we have an epimorphism of compact Riemann surfaces, and in that category, all morphisms are really epi, so surjective. In contrast with field extensions, or category of fields, where all the extensions are mono. Again, showing that there should be some duality here. Then the ramification index of this morphism which let's recall that is an integral, a total sum over the points of ramification. Which again is associated with the morphism. And there was a discussion last time if I can use the term of divisor, which in some sense is specific to one Riemann surface, without mentioning that the morphism. So the morphism defines two divisors, which we can call them, say, ds and dt, to emphasize that it's associated to the morphism, or with the morphism. Use this notation. Also, at this stage, you might try to think of again, category theory or a grade or input for this context. To think of a TQFT in the sense of a TIAH, 1 plus 1, and then we would have a surface, say, sigma plus, with a divisor, and I don't know if later this would help. Then a cobordism between these two. Manifolds with the divisor, or manifolds with boundary as points. Also note that here the dimensions are complex. When you consider real, then of course you have the even dimensions. So the index is defined as the integral of E of P where this is later called the difference. So I'll say integral of difference, which I didn't know much about it, but I learned that it originates with the algebraic number theory, and it was by Dirichlet and so on, has to do with prime ideals, say the problematic of ramification theory, so ramification theory in the algebraic realm. And in characteristic zero, this is the same as EP minus 1, where EP is the index of ramification at a branching point for one point in the fiber. So actually, index of ramification at a ramification point over the branching point, minus 1. This almost holds in characteristic P also, but if, with the exception when EP is congruent to 0 mod P, which is again not essential here. So coming back to the interpretation of this Riemann-Hurwitz formula, the difference is also like a difference of dimensions, if you want. And the index is, ramification index is the integral. And if you think of TQFTs, then these divisors are interpreted as boundaries, one-point compactification of a boundary. One may think in this way. And the theorem says that this ramification index is the difference between the Euler characteristic, let's call them like Euler-Poincare characteristic map for the two surfaces. Now, it starts to look like a punctorial statement. So let's brainstorm a little bit right now. So you have the category of these Riemann surfaces, then these morphisms. Then with each Riemann surface, we associate its Euler characteristics and here we call that the Euler characteristic of a chain complex. It's the alternating sum of the dimensions. And the theorem I mentioned earlier, which is just linear algebra fact, says that this is the same after taking the homology. So at this stage, I would emphasize this fact that the other Poincaré map is homology invariant. Which of course is known in the algebraic topology setup, but which is just a linear algebra fact. In some sense, when you prove it, you see that there are some like difference or the effects differences of dimensions which cancel each other in this alternating sum. So one wonders if such a similar phenomenon happens here, but not just at the linear algebra level, but because of the topology of the base. So there's just like a hint for later to think about it. Also know that dimension is dimension of vector space or a field, the classifying invariant. Because we want to see how these invariants relate. And as another remark, the degree of an extension, field extension, or field morphism. Because here we'll have this phenomenon of changing base ground fields. The degree is multiplicative on extensions as on paths of extensions. And then, of course, one would want to look at the functor, changing coefficients, and then see if there is some kind of derived functor result behind that. And how much of that derived functor result is, in fact, this Riemann-Hurwitz formula. Because when we take here the other characteristic, I think that first you might take like singular homology or some other algebraic topology technique, like triangulations of Riemann manifolds, or even better, Hodge in a Hodge Theorem context. One may look at homology bases and harmonic flows. And of course, the Rama isomorphism and the associated periods, which are also a very important concept targeted by this my recent research, trying to understand beyond algebraic numbers, these periods, and how they capture the geometry. And again, here's exactly what we're trying to do. Here we have the number fields, algebraic numbers, number extensions, then function fields. Probably we have to look at changes of coefficients, so morphisms of number fields, and see how the geometry evolves. And that's that should be similar to how prime ideals split under extensions, so under morphisms. So over there is the ramification theory in algebraic number theory. But then if we want to see or to understand in a similar way here, we look at ramification under morphisms of the corresponding of Riemann surfaces. So again, it's a clear duality which we are trying to understand. And one more thought over here. If we're looking at Theorem and harmonic flows, then we should connect with what I said earlier in mentioning the Poincaré theorem, vector fields, indexes, and sort of the tangent bundle picture, which here, of course, is the line bundle for these Riemann surfaces. With this, I'll take a picture of the board. Take the one, take 2 minutes break. 1 minute. And continue with the results. So that was slide 20. Then there is something new for me, which I didn't have time to look more into it. The correspondences. So correspondences and Riemann formula. Let's start with the definition. A correspondence between two algebraic varieties S and T is a subset which is a union of subvarieties. So I'll just write as the two arrows from gamma, the subset in score C. but clearly is more than a subset, more like zeros of a system of, let's say, polynomial equations which are not irreducible, so it breaks into various irreducible subvarieties. Again, that's not my area of expertise. George would be nice to be here, but it's not today. So also, if you think of ideals and all that, then it makes sense to have these. I mean, I don't know exactly how to make sense of this graph, sort of a graph, more like an extension of a graph, because earlier we looked at morphisms between varieties, between Riemann surfaces. And now we're generalizing by looking at these correspondences. So for such a morphism, we can talk about the graph of phi inside H cross C. Also, this kind of framework is reminiscent of localization, of course, and you have categories localizing morphisms. Right now, I can't say much more about that. On the other hand, I want to bring in this discussion the idea of Zariski topology, which was a very good tool at the level of commutative algebra and the development of classical algebraic geometry, following the new topology introduced by Poincaré, 1900s. But then it became clear that the point set topology plays no role, and you have to somehow remove it and go from topology to retain the network. I use the term network because it's more modern and more important in all areas, in sciences, mathematics. Think of quiver varieties, representations, Mackay, and all that. Atlases, they start to look like Rothenic covers in the categorical setup. So we're moving away from the point set topology and topology itself. Therefore, Zariski topology, I would say, needs to be interpreted in a different way. And I remember that it's about there's a relation, I'm not 100% sure right now, that the closed sets are unions of points. So as if the divisors are really the essential objects which should be taken into consideration, at least when we talk about curves dimension 1. Otherwise, it's more complicated. You would have several, like a filtration. But at least for Riemann surfaces, then divisors, the points are the closed, or correspond to these closed sets from Zariski topology in the commutative algebra setup. That's my intuition right now. So this is what I try to convey on the slides by saying mathematical trends evolved from analysis, topology to algebra, and so on. And then the general results due to Zoiden is the following, which is a generalization of Riemann-Hurwitz formula for correspondences. Due to Zoiden, 1871. Is that given such a correspondence, and I change the notation a little bit. So more correspondence from T, or between T and T prime. Then the ramification index, like a total integral that I was suggesting earlier, minus the degree of the map, which is the generic multiplicity of the fibration. No, sorry, minus the product of degrees, because here we have two morphisms, phi and phi prime. And then this difference kind of suggests, is reminiscent of a failure for this for a functorial map to be multiplicative, like lack of homomorphism property. So this difference again, I'm thinking here, if you have a short exact sequence, if it's split, then there is a way to characterize the relation between the split case and the short exact sequence, second homology, and all that. So here, the difference is constant, which here means same for T prime. So if you fix T, doesn't matter how you change T prime, as long as it's in correspondence with T. But right now I realize this I'm not sure to what sense constant is. So note ramification index of what? Of phi. So depends on phi. Then if you change the morphism, but keep actually I take it back. Depends on gamma. I'm not sure how to phrase it this point. You consider all possible correspondences. I don't know at this stage, so let's just move away. And I was noting also that the degree is also another Poincare map. So there is some quite general homological algebra fact here, independent of the specifics of Riemann surface varieties and all that, which we might want to discuss later on. I wanted to see some examples of correspondences, but didn't have time to do that yet. So now let's move at the next important level. What about the symmetries of these objects, Riemann surfaces? And we have first, let's mark this. Which means if we have our morphism to then be analyzed from the ramification point of view, then we have the loops at S, loops at T, the automorphisms, their symmetries. How does the morphism connect to this? Connects these two automorphisms. And of course, one might think immediately of pi 1, whether it's topological, algebraic, fundamental group, but rather as a group weight. So again, a category of Riemann surfaces. Marker doesn't work, so yeah. Then you have S, you have T, and the morphism, as if it's a path from S to T. And by the way, in my abstract algebra class, I was starting to use Venn diagrams to picture categories and morphisms and constructions between them, which we call functors and so on. And obviously that is one level higher because here points are objects and so on. But then there's like a topological flavor for all these pictures, which invites the use of algebraic topology, but at the categorical level. which actually connects with what I said, that there are some homological algebra facts, general facts formulated in terms of category theory, which are independent on the actual point set topology of or bulk points from these manifolds. So back to here, with such a picture, the objects will have some automorphism, which play the role of pi1 based at S, pi1 of the category. Category of Riemann surfaces, Algebraic curves, etc. Based at S, then there should be some isomorphism with pi1, at least in the topological case. Riemann surfaces based at T. But here, we don't expect such a nice behavior as in the topological case, where the fundamental groups do not depend on the base point, and in the continuum case, they are isomorphic through conjugation and so on. So what about their symmetries with this in mind? And we have the following. First result by Francis, de Francis, in 1913, which says that for Riemann surfaces or algebraic curves, but in genus greater than 1, which of course means removing sphere, but again, torus, which is flat. So those are the spherical and Euclidean, if you want, geometry cases. In higher genus than 1 hyperbolic case, then the automorphism group is finite. And just a couple of minutes more. Then later, Hurwitz, or maybe I misspelled the name, gave a bound for the size of this automorphism group. And again, I want to write it in terms of Euler characteristic. Of course, it's 42, the answer of everything in the universe, times the Euler characteristic, the corresponding Riemann surface, which should have to do with the Poincaré-Hopf theorem somehow. And here, of course, there is much, much more if you start to connect with other areas. Namely, Belyi's theorem, which we'll talk about that next time, has other important results associated to it. Namely, that these algebraic curves can be realized as modular curves which means we have to look at congruent subgroups of SL2Z, which is the modular group controls really the arithmetic and algebraic number theory, and then has this geometric counterpart, and is related to tessellations of Riemann surfaces, descent d'enfant, and all the good stuff connected to this Belyi theorem. So let's stop here and come back to review this part with symmetries next time, and an overview of Belyi's theorem, and then continue with Oort's article, trying to add some more insight into it using category theory, and as I said, and Grothendieck's approach to modern algebraic theory. Thank you.